Hi, my name is Jazmine Afolayan, and welcome to my presentation on the future of stroke rehabilitation, a layman's approach. This is a layman's approach because this is a research paper that I developed in my senior year of high school with very, very little experience. And so you can think of it as a premature challenge to the field or like a hypothetical analysis because it's really how I understood the information and then myself responding to it. And so this paper is investigating how stroke rehabilitation could be improved. And I researched this topic because I have relatives of my own who are affected by neurological illnesses. And so the two main important vocabulary to go over are neurogenesis and neuroplasticity. Now, the divide between these two processes in the field are pretty blurry. However, neurogenesis is just the development of new neurons, while neuroplasticity is the brain's ability to change. And so you can think of neuroplasticity as a process that happens on quite of a larger scale, and it's really between neural systems or those group of neurons that work to produce a skill. And so going on to the current research is basically saying that neurogenesis cannot occur in adults. It stops at a certain age. Once a neuron dies, it's dead. And also I found that, current stroke treatment measures kind of focus more on neuroplasticity. But then I started to have questions. Could neuroplasticity have side effects? And also, is there any way to make stroke treatment a bit more fun? So when neurons die, the brain has the ability to reorder itself. This is essentially neuroplasticity. And how stroke researchers use this is that say that a patient lost a skill. What they do is they train the brain to redevelop that skill. And what happens is the brain is reorganizing its systems to strengthen the connections between the neural systems, which then redevelops the skill. But I kind of had my questions with this. So why strengthen the connection between two weakened systems? I just saw that as counterintuitive. And then also, what happens when too much information shifts from system to system, or when the balance of connections is kind of thrown off? Could neurons experience an overload of information, and how would this affect them? So I wanted to find an alternative to neuroplasticity. Could we actually revive neurons or just use neurogenesis, the other process, instead? And so this is the backbone of my reasoning, and we're going to focus more on this point since it's kind of the more complex point, and also it's more based on my own reasoning. So I'm countering neuroplasticity from this evidence specifically. Neuroplasticity might not actually benefit all patients post-stroke, depending on their circumstances. So now we're going to try to find an alternative to neuroplasticity. And so I want stroke researchers to consider two changes in the current stroke treatment measures, but we'll focus on this first one. Focus on neurogenesis over neuroplasticity. And why is the case? It's because hypothetically, the result would be that stroke patients have a fuller recovery after stroke. So to break this down, let's look at a hypothetical pro of neurogenesis. Let's take this scenario. If neuron A dies, can neuron B develop the same information as neuron A? So what's happening in this diagram is that neuron A is dying. However, it's recreating itself as the brain is kind of undergoing a new experience, or I should say the body is undergoing a new experience and it's affecting the brain. So a new neuron develops, but from a different experience. And so one question we'd have to answer is, do neurons just grow after a cognitive skill is worked? Let's take a stroke patient that has lost their memory, for example. If they were to continuously play chess and engage in that activity, which is different from a normal activity they would do, would they develop a whole new neuron that is based on a different experience? And really the slogan for this is different inputs, but same outputs. And so comparing this or neuroplasticity to the previous slide, we see that with neurogenesis, the same count of neurons is preserved. 3 in total. A just becomes B, but it's the same information. However, how I understand neuroplasticity is that neuron A is dead, but through a different experience, 2 neurons, C and D, survive and are strengthened. However, there's still a greater quantity in neurogenesis. And so now on to implementing these suggestions. Of course, we need a lot more research since this is really just based on a layman's understanding of neuroplasticity and neurogenesis. So how do experiences or activities affect the brain on a molecular level? Can things such as are as so simple as playing chess actually affect the brain all the way down to the neuron? Is there a greater benefit, or is there a benefit to having a greater number of neurons? And also, do individual neurons carry their own specific information? If there's no benefit to having a greater number of neurons, then neurogenesis might not matter that much. Also, if individual neurons don't carry their own specific information and are actually all homogeneous in one system, then it might not really matter if one is lost. And these are the references that I use for my paper, which I will summarize on my repicture profile. Thank you.